Recording now. And welcome back to the ICOG event. We had one also 2 days ago, but unfortunately I had to multitask between two, so I couldn't give you a proper welcome to the ICOG event series. So I'm very happy to welcome Lorenzo Cominelli, who is a postdoc researcher at the Piaggio Research Center in Pisa. I had the pleasure to meet Lorenzo last year during the Living Machines conference. I think it was the 10-year anniversary, maybe edition. We were together at the neurorobotics workshop, and there he first presented Face and Abel. And so those of you that know me and know that what my research is on, you can easily see why it was very, very fascinating. So Lorenzo's research is focused on AI and cognitive systems for social robots, and he has a particular interest to the influence of emotions in the robot decision making. And so he has been responsible for the design and development of the Face robot's cognitive system, and also in the last year worked on the development of Abel, which is the hyper-realistic expressive robot. Abel has been born in a collaboration between the Piaggio Research Center and the animatronics creator Gustav Högen. So with that, Lorenzo, the floor is yours, and please.
Thank you, Anna. Thank you for your kind presentation, and I'm very excited to be here with this talk. I will use these two robots as an excuse to talk about a lot of things and points that I want to discuss with you. And of course, it will be not a showcase of what we do and what we think about cognitive systems, but I mean, it's just an occasion to discuss some points. So I will use some experiments and things down to discuss these points. So let's start from the beginning. So let's start from Face. Face is an expressive robot. It stands for Facial Automaton for Conveying Emotions. I started my thesis and my doctorate with this robot, and it means Facial Automaton for Conveying Emotions. Actually, it is born only as an emotion inducer, so as a physical representation of expressions and emotions. And the mechatronics has been done by David Hanson, so the one who Sophia. She can be considered as an older sister of Sophia. And she has this 3D printed skull designed to host servo motors. So of course, this kind of robot differently from ICAB or now has this facial possibility of expression. And this is based on the study of Paul Ekman, so the facial action coding system so this scientist has grouped the muscles of the face in action units, and these action units corresponds often to a single motors or a combination of two servo motors that are inside the head of the robot. Face has been used as a tool for therapy in children with autistic spectrum disorder, and it has been involved also in the EASL project, a European project in which the robot has the role of a synthetic tutor that has been used in this personalized learning with children with some attention deficits. So let's start from the big picture, the face cognitive architecture. The schema is a bit old, but the fundamentals are still the same. And you can see that the distribution of the main blocks, so the sense, the plan, and the act block of the robot are distributed in a hybrid way. Here there are some properties like hybridity, the usability, maintainability. Many properties are a consequence of the modularity of the system, which is also given by a software that you developed, so a middleware that you developed, which is the YARP middleware. And well, obviously this is just a conceptual division because they are computer programs, applications that are distributed in different machines, different computers. And I will discuss a little bit about sense and the actuation part to focus more on planning. So the cognitive, the high level cognitive part. Let's see let's start from perception. So we have this system that perception system that we developed that is called the scene analyzer. It's based on the Kinect, and as you can see, we have an integration of a lot of information. So this is an application that integrate the results of different algorithms and softwares. We have the information provided by the Kinect, so the 3D position of the joints of up to 6 persons. We have another software based on CNN network, convolutional neural networks that extract the facial expression, and also something like estimation of gender and age. What else? We have another software that takes this pink point that is like an analysis of the bidimensional image, so just like about contrast and bidimensional features of the image. And well, what the robot actually see, this is just a summary of these features that the scene analyzer extracts, is this. So a file, an XML file, so structured information about what the robot can perceive. Here I highlighted some points. As you can see, we have, for example, the speaking probability of that subject, the ratio, so the possibility that the subject is performing a happiness expression or an angry expression, and we have some raw data like the three-dimensional position of the joints. We have also the saliency point, which is this point that is taken from an image analysis. So this is the structured information that will be given to the cognitive system. This can lead also to an immediate reaction in the actuation. So this is why it's also hybrid, the system. And let's go to the other part. On the other hand, so we have a perception, so an extraction of information from the social environment, and then we have a head and face that need to be actuated. For this actuation, we use, you can see here, this robot animator interface. So each slide corresponds to a single servo motor of the facial expression. And how we perform this, we used to refer to an anatomical map of facial expressions and save in this bidimensional space of emotion, which is the circumference model of affect of Russell, in terms of valence and arousal and an expression, so an emotion that the robot can express. Starting from this point, so performing an interpolation of scattered data, we fill the entire plane so that each point is meaningful, so it corresponds to a configuration of this facial expression in face. This is very useful, first of all, for having a kind of dynamics of facial expression, so we can change expressions without, of course, going back to the neutral and then to the expression that the robot has to perform. And let us also see some, let's say, produce some compound emotions going in between these fundamental emotions, and so working more on micro expressions that would be very difficult to realize manually, let's say. So initially the face was just, the robotic part was just the head, this rubber mask. This has been mounted on a passive mannequin for application. For example, the first one was this one with autistic children. And we also try to build a body for that robot, starting from the InMove project. I don't know if you already know this. Is from a French engineer, I think. So it's this open source project where you can 3D print parts of the robot. And we also integrate these hands that have been made by an Italian startup. So this is like a modification of the InMove hands, and works like a telephone for deaf-blind people. So it has been modified to produce science. This is, we say, a social body that is conceived for communicating. So this kind of hands, for example, are not good for grasping or for force actions or for manipulation of objects, but are very, are good for representing science in communication. So it was what we were looking for. We also changed the body for embedding the new version of the keynet, and a few modifications of these bodies. For letting the robot know some gestures that can be performed during nonverbal communication and interaction, we can use, as we have seen before, some manual control. So like modifying the single motors for performing gestures and then save them, so that from the cognitive system we were able to perform these gestures. Or we can use the softwares that we developed, like the scene analyzer, to make the robot imitate this kind of gestures. I have this video in which a colleague of mine is teaching, let's say, some gestures to the face robot. As you can see, it's not very satisfying, the aesthetics also of the robot. I don't like too much when I see this kind of mixed robotics. No, we have skin-like parts, we have these more plastic things. So this is one of the reasons why we also go to the production of Abel. I have also, I think, a part on, yes, this is, we use the leap motion, which is a sensor, is like a little kinect for the hands to let the robot imitate and say some gestures of the hands. So let's go through the cognitive part. We have this abstraction of features and information from the social context. We have a robot that is able to perform some gestures, some nonverbal communication by his body and his facial expression. So how can we use this information? For this, we rely on a kind of systems, of artificial intelligence systems that are expert systems, which are not a novel thing. It's something that it comes from the 80s, but I will not spend too much time on this slide, because I think that many of you already knows what expert systems are. But you know that usually you have a human user providing facts to this kind to the system that has inside a knowledge that is based mainly on if-then rules, that more than through more conventional procedural code. And there is an inference engine that is responsible to manage the execution of these rules. So this kind of system will react with an expertise. So why we decide to use this kind of system? So to make a comparison, for example, between machine learning and expert system. I wrote machine learning and expert system here, but you can read also data-driven approach and knowledge-based approach more generally. So this, generally speaking, we know that machine learning, you give to them, to this kind of approach, you start with inputs and with answers also. So you do a training with a data set, and this kind of system is able to find his own rules. I put these brackets here because most of the time are not explainable rules. So they are not rules that are directly grounded with logical reasoning or something that is explainable. On the other hand, knowledge-based systems, so expert system too, you give the input and the rules to the system, and the system gives you answers. So this kind of difference, I think, is very important also for ethical aspects, no? Because you know that in this case, in the first case, you have all the responsibility on the data that you provide to the system, while in the expert system, you can have a control of how this data would be managed. Of course, there are pros and cons. There are applications that needs an approach or another, but I think that a combined system, so using machine learning and using an expert system afterwards, can be a nice solution, because with the data-driven approach, we can extract. They are very good for learning, where they are very good for feature extraction and classification from real world and raw data. But then we can use this information in a high level way. So we can use this information for abstract reasoning, for emotion processing in terms of emotional concepts, and to perform some contextual decisions on the situation. So our idea is to embed an expert system in the high-level cognition part of a cognitive system, with, of course, not having a human user giving the facts to a system, but being the robot itself that autonomously, thanks to the sensors and the processing of the sensors, is able to extract from the real world some facts that then can reason on these facts, and have the actuation, and so the possibility to respond to this reasoning with actions that change again the words and close this loop. So, graphically, I used to imagine this kind of rules as this representation. So you have a lot of conditions. They are sometimes called antecedents. So you have these facts that can trigger, if they are all true, usually, can trigger the left-hand side of the rule. And in the right-hand side of the rule, you have always also a procedural part. So you can have a list of actions that the robot can perform. But you can have also the creation of new knowledge, of new facts, for example, that can be, of course, in the left-hand side of another rule. This is the way that we can use to do reasoning chains, so to do inference. Usually, you can use dummy facts, so facts that are created just to trigger other rules, or you can modify some structural facts that you have in your factual knowledge. This is cool also for making the robot change its mind about things that it has understood from the context. Or you can also, thanks to this embedding, run functions that immediately execute actions. So here, this is just a graphical representation to say that you can perform more complex reasoning. So also the time scale can be different from the perception of something to the execution of an action, or to a new conclusion in memory of the robot. And or it can be very quick and simple. And another nice thing of this kind of system is that without changing the code, you can change the course of the execution. For example, changing the conflict resolution strategy of the rules that are activated, giving priority for the simpler rules, or for the rules that have been triggered before or after. So you can do some nice experiments, changing the way of reasoning without changing the chunks of knowledge. Yes, other features of these systems, you can perform forward chaining and backward chaining. So this is similar to do deductive reasoning and inductive reasoning. So you can reason from the facts to the conclusion resulting from those facts, or in reverse. So it can appear in the mind of the robot in an hypothesis, a potential conclusion, and the robot look for facts that can support this hypothesis. Of course, these facts and this information can be considered as completely true or false, or you can use some fuzzy logic, Bayesian logic, like for example, introducing some certainty factor or information, some likeliness of necessity, likeliness of sufficiency of facts that determine some conclusion in the reasoning. So here we are to the plan block. As you can see here, there is the Metascene, so the file that is given by the scene analyzer and streamed to YARP. That can be analyzed by different modules. Of course, modules are like sets of rules that are deputed to different functions. Like there are rules for the attention of the robot, so where the robot has to look at, rules about the emotion of the robot, so the phase that has to perform, and also the mode. I will explain in a few this split, this division. And oh, this is another thing about the consumption of the robot. This is another example of the hybrid system, because we have this power supply that can directly change the velocity of the movements of the motors of the robot, but also can become also an information that can bias some decision inside the cognitive block. So this is another way to see another point of view, another view to see the plan block. And I think this is interesting, meaning that the Metascene contains some information that is analyzed by the system in a first stage that we call a primary cognition. Why? Because we have templates. Templates are like classes in object programming. So we have this sort of structured concepts that we can use to make a check, you know, of the information that is coming to the cognitive system, and to understand if this information is related to something that the robot already knows. You can use also truth ranges of the features of a template. So you can, for example, distinguish that if we have an information about a face, but we don't have any information about the body, so that would probably be a picture, not a person in front of the robot, and so on. And you have to pass this stage to go in the fact list. So meaning that I perceive something through my senses, but I can recognize it as a concept in my mind. No, this is why we call this a primary cognition. And once it's in the fact list, a concept it becomes an effect in the mind of the robot and is analyzed by the rules engine. No, so it can trigger rules. And as I said before, you can have a change in the behavior of the robot, but you can also have the production of new facts. So perform this abstract reasoning on abstract information. This is an example. You can also have a bit of control in the execution of the rules, putting some saliency values. So you can, let's say, design these layers in which rules are concurrent, but you can be sure that once this process has been finished, you pass to another kind of analysis or planning. Here you can see one of the rules, for example, to check the presence of a subject. These activate the tracking of this subject, asserting this fact, which is in the left-hand side of another rule. And we, for example, simply look for some significant gesture in the person that is in front of the robot to react with a facial expression, or and to modify the winner of the attention of the robot with that subject. Of course, this is a look rule that look if someone is raising the hand for asking the attention. We have many others rules that are competitive with this one. But when we are sure that this kind of things has been done, we pass to action. And so we set to the robot, okay, the winner is that person. This is the most suitable expression to do is in this social context, okay? This is an example of an interaction, and you can see here some behavioral rules that have been done. You can see also that there is, this is the animator, this is the consumption thing, this is the scene analyzer, this is an older version here. And why I'm showing this is just to to say that you can see that the robot is performing some typical things that in nonverbal communications you have to do, like turn taking. There is something about proxemics. So there is a moment in which I approach the robot and I enter in his intimate space, so you can see this kind of reaction, like this annoyed face, and the attention goes to another subject. But what is the problem here? At this point, the robot is still a situated agent. So it's something that can understand what has to do, what has to express in a certain situation, thanks to its sensors, to its reasoning about the context. But there is a functioning that is missing. So it doesn't use these emotions. It's just reacting with emotions to the context. So we need to exploit the emotions that are expressed by the robot and felt by the robot, let's say. And for this, we took inspiration from neuroscience, and in particular from Antonio Damasio, and from its somatic marker hypothesis. So what this hypothesis says that, I mean, he's a neuroscientist. He performed a lot of experiments on impaired patients of a very specific region of the brain, and hypothesized this function of the ventromedial prefrontal cortex, which is an area of the brain that performs this association. So it's like a link between the body and the mind. And the somatic marker is also understandable also by the name. So it uses the soma to label, so the body to label inducers of emotions. So you have an object, an event, and a somatic state in a human subject. When this somatic state becomes relevant, this area of the brain, let's say, that create this association, this somatic marker. This area is connected to many other areas of the brain, like the amygdala, the thalamus. So you have this kind of connection. And so this is the labeling phase, and then you have the possibility to have a recall of this marker. So what it means that if I recognize the same or similar object or event that makes me feel this bodily sensation, I will have a sort of optimization in my decision making, meaning that the choices that I could perform will not be the same, but I will be suggested by my body to understand that something is good or not for me. Okay. We also took inspiration also from this vision that the Mali have about the theory of consciousness. So it's like this. This how can I say, constructivist vision of the self, or also of so starting from a simple perception of the body to a core consciousness to an extended consciousness. So everything is given by, let's say, a merge between an internal and an external representation. This is why we divide the emotions and what we call the mood of the robot, because we need, first of all, a different also time scale. You have these emotional reactions performed immediately by the body of the robot, and this is not good for biasing the behavior of the robot. So we also divide this. We also create this other internal representation, which is the mood of the robot, that can be modified in a more gradual way by events. So, for example, practically, we will have rules that determines that in a certain situation, I will have to perform a certain facial expression, but this will change the mood in a gradual way. For example, given 0.01 to the arousal and minus 0.02 to the balance. So we have all this contribution of different rules and different emotions by the perception of events in the context. And so you will see like discrete and quick movements of the facial expressions, but a more slow and gradual movements of these modes. And we also put to emulate this somatic marker hypothesis. So we put thresholds in the moods so that if the robot, let's say, is in this safe area of feelings, so if we are in this white area, it doesn't create anything. But if we go in this red area, so after a certain threshold of emotions, so we take the modulus of balance arousal of the moods, then the system creates a somatic marker. So we have this somatic marker rule set that look at which is the mood of the robot, which one is what, let's say, draws the attention of the robot, and if this happens, it associates that entity with that feeling, let's say. We tested also this kind of system with the Iowa gambling test, so with a simulation of the Iowa gambling test to see if it works, and then this has been integrated in the cognitive architecture of the robot, becoming this SEAI, which is the social emotional artificial intelligence. You can see here that the contracted parts, so this is the sense part, this is the activation part, and we have this creation of the representation of internal and external stimuli, and the coexistence of these two aspects can bring to the creation of information that are higher and higher level. What else? So to say immediately something that this is, I think, a nice solution to have a good control of what is happening inside the robot, meaning that I can determine exactly what object or what person or what event or what gestures or what kind of sentences determine exactly what kind of movement, let's say, in the mode of the robot. But this is very complicated because we don't have this kind of knowledge about I don't know what is exactly the reaction of I don't know to a kiss, to our emotions, and these are very different according to person, but this is a method that can give some advantages for this kind also of control, also by an ethical point of view, if you think about it, no? Because you can say how the robot should think about what is able to perceive. No? This has been tested with a real human-robot interaction scenario. So we have this interaction. We instructed these colleagues to have a biased interaction with the robot, meaning to be polite, to be unpolite, so to be not kind with the robot, without saying exactly, of course, what they have to do, but like simple things like saying hello to the robot, like talking to the robot, ignoring it. So starting from this common sense social, let's say, behavioral norms, we let the robot interact with them, and we can see that the robot is able to not just to change the emotions that needs to be expressed, but we have also change in the mode that here is represented as an emotional state, so the modulus of balance arousal, and having a threshold only when, for example, this subject doesn't manage to reach an important consequence in the emotions of, in the artificial emotions of the robot. But if this threshold is exceeded, you can see that the same, I mean, first of all, a marker is created with the values that is related to the balance of the emotions felt by the robots. And the same balance and arousal representations is immediately performed again when the robot can see again can perceive again the subject that time invoked this emotional state. So we have a bias in the behavior without having a reason that is given by the social context, but is given by the experience, a sort of emotional experience. Oh, let's pass to the new thing. So Abel. Abel is our new robotic platform. And as you can see, it has the appearance of a kid, of a pre-adolescent. No, I would say that it has like 12 years or something like that. This has been done in collaboration with Gustav Hogan from Biomimix Ltd. And all these are robotic parts, so it's just the upper part of the body, but all these are robotic parts. And we have 43 servos, so 22 to move the facial expression, 5 for the neck, 5 per each arm, and 3 for each hand. What I want to underline here is the fact that there is a very deep study about anatomical movements in the mechatronics of the robot that I hope that will lead us to perform very realistic, for example, gaze movements and mouth movements, for example, for emulate speaking. So the movement of lips and mouth to represent what the robot is saying. It has some sensors embodied. Here you can see an HD camera. It has binaural microphones in his ears and a speaker inside the throat to, of course, to produce speech synthesis. And another thing that I want to underline, I think that you will probably agree, is something that I realized in the making of these robots, as you can see in this picture, and is that there is, I think, a huge need of involving this kind of artistic professionals, because who is Gustav Hogan? And Gustav Hogan is one of the most requested collaborators for Hollywood, for movies, so special effects, animatronics, and I mean, as you can see here, this is Livia Turco. She's a sculptor. I think is the right word for it. And she manually designed and made a statue. Okay, so we decided the aesthetics of the robot. We can also discuss later if you want. But we decide how the robot should be, and so this master has been handcrafted. No. And this is very important. Another thing that is here, you can see, yes, the production of the molds, the casting of the flash-like materials. This is another thing that is very important. So the material it has a great responsibility for the realism of the movement. No? So we test different solutions for the composition of this flash-like material. And this part is about the mechatronics. So there is, you can see here this anthropomorphic inspiration. So the inspiration to the anatomy of the movements of the body of the robot. Here we are visiting in London for following the work. And what else? Oh yes, that these kind of professionals. What I wanted to say is that these people has the knowledge about how to create these, how to build, manually build this creature, and how to move them, to control them, so to create, to induce emotions in an observer. No? So this is, I think, a collaboration that is very important between technical and professionals and creatives. You know? So having such a complex structure, I will try to say where we are now, what are our intentions and future steps, so that we can also discuss this. And what I was saying is that having this complex structure and being so yes, handcrafted this robot, we need also to apply some reverse engineering, like moving the neck manually, removing the torque from the motors to understand how to move these motors. But I mean, the results are quite surprising, meaning that the movements are very realistic, very fluid. This is also due to the servo motors that we are using, is the dynamics of motors that are very silent also. And okay, I will go very quick here. This is something that we make with a student, and it's let's say a way to teach to Abel some gestures, manually moving his body. And we also have tried to understand which is the best way to control these robotic arms. We use the inverted net profile, and we tune some parameters to improve the human likeness of the movements. As you can see here, we have a comparison between different velocity profiles, and you can see here how better and how more human-like the movement is. No, so we have tested different values to understand what was the result. We are very satisfied. Oh, these parts will also be covered with skin. So we just use this. We keep them uncovered because we need to intervene on the motors and to, of course, work on these movements. And okay, this is not so important, but anyway, we have done all the first steps that are needed. So security, so having some compliance, and some maximum force that the robot can apply to ensure a secure physical interaction. This is some inverse kinematics for avoiding self-collision of the robot. So we use this ROS module to yes, to avoid the possibility that the robot can report some self-damage moving and have some cognition about where the arms are. Okay. For the expression, we start again from some. Here also we try to put this whip on Abel. So for the expression, also we start from some fundamental facial expressions, doing the same work that we've done with face, but with a doctorate student, we are now thinking about let Abel learn expressions, and most of all, we will use this database, and we are collaborating also with an Italian startup, which is Emotiva, that is able to extract also single action units of the facial expression to train Abel in following as good as possible people speaking. Okay, so we want to understand how to move the single muscles, let's say, of the mouth, following the movements of facial detection of real people speaking in these very controlled scenarios. What else? Oh, I want to say something on personality and trust also. So another work that we are doing is about personality, and also here we have found a theory that we liked, which is not this one. This is just the Myers-Briggs types indicator. I put here to say this. Personality is often, if not always, studied with, let's say, I can say a top-down approach, meaning that from the external we do questionnaires. So we write questionnaires to people asking how they react to different situations, or how, as you can see in these dichotomies, how they face some problems, for example, or some situations. And according to these answers, we put them in some boxes like this 16 types of the Myers-Briggs. It is almost the same with other approaches like the Big Five or the Exaco. And I mean, this is very interesting and very useful and working for psychology. So you can, let's say, understand how a person will probably behave in a certain situation. But I think that these kinds of approach are not suitable for designing a personality in the robot, because we need to have a bottom-up approach. So we found this theory from Michel Schodal that we like because of this different approach, which is more bottom-up. So it's the cognitive affective processing system. So they describe personality not just as a reaction to specific situations, but as they try to discover what is in the black box, no? So what is in the person's mind, and they describe it in a different net of cows. So these cognitive affective units, which, if you see, are the same, let's say, concepts and fundamentals that we use even in social robotics. So we have encodings, we have beliefs and expectancies, we have affects, goals and values, and competencies. So they also take into consideration the fact that a similar, I mean, two different persons with the same personality can have also different emotional state in that moment. So can change their attention in the features extracted from a situation. And for example, some links between these units can change according to the emotional state at that moment, leading to a different behavior. So we have, of course, recurrent behavior that are let's say, the personality types, but we can have also deviation, and they try to describe this inner cognitive and emotional process. We have done, let's say, preliminary work with the students that designed two different personalities and tested using the same situation, providing the same situation to the robot, and to see how the system works. This is just, let's say, a test of the implementation of these things. Now we have in program two with psychologists from the EMT, Luca, to design and evaluate these personalities implemented in the robot using this chaos network. But again, we don't have the knowledge about how these internal processes work. So we need to ask to people. So we are in program to design some questionnaires that have to be administrated to a lot of people to extract what they think that about the internal process of other persons, and we will try to apply this kind of theory for controlling the robots. Try also to understand, first of all, if it makes sense that a robot has a similar personality to a human. I will say yes, just for recognition of this personality. And also to, I mean, I think that there are many interesting applications of this approach and this personality thing in several contexts. For example, to understand, to do a kind of optimization of the right personality to use in an interaction. So this is something that would be extremely useful in human-robot interaction in general. Yes, optimization, for example. I've talked about optimization because I guess that the robot is able to understand very well, which is the emotional state of his interlocutor. But this is not something that is easy to do, as you know. So we are thinking of extending the perception of Abel, thanks to the presence also in our research center of an entire team that is responsible for affective competent expert in affective competence. So we already have some interesting devices like this wireless EEG helmet. There is a student that is working on the analysis of thermal images. So, for example, they are quite good to understand if a subject is in a stressed state or not. But you can also, let's say, categorize and classify some emotions from the distribution of the blood duration in the face, but you need that it should be very stable. I mean, it's not so easy. Anyway, many approaches and many, let's say, also physiological parameters, many parameters can help in an assessment, a more reliable assessment of what the subject is feeling. Also in a known, it's something that is not perceivable in an audiovisual system like the one that is embedded in the robot. And we have to remember that the robot is also a computer, so it can be connected with distributed objects that are aware by a subject or distributed in the room. Of course, again, no expert systems here, no knowledge-based approaches, but machine learning techniques to extract and classify what this kind of devices are able to give us, to provide us. And this is, I think, the last thing. Okay, I am in the time. Another experiment that we have done recently, this has been published previous year on Scientific Reports. So we have these experiments of an economic game with the face. We use face in this case, and so what we have here, we have this kind of economic game that is based on assessing if a subject has trust in another, because you have an initial amount of money. And I mean, I will not go into the detail, but let's say just that it is a game in which the best choice for the players is the collaborative choice, not the collaborative choice. So, but to let this happen, one has to trust another. So we test these applying a variation of sharpness on the trust game, where the two players can pass a message, so it can communicate before taking these double-blind decisions. And it was interesting because we test different aesthetics, different embodiment, let's say, of the player B, which is face, which is an actress that replaces the same actions of face, and let's say a computer box, which is this Alexa-like object that just have lights and speaks. So this is something that we perform, also trying to understand what is happening inside the bodies and the feelings of the subjects using the extraction of electrodermal activity. And we found that, oh yes, in this variation, we want to see if the robot promise that will be collaborative, if there is an effort in the other player. And what we found is that it doesn't have, there is no meaningful difference about the content of what the robot or the other entities are saying. So if a promising message or an empty, just logical message, but it becomes meaningful when there is an emotional involvement intended as electrodermal reaction, and when the subject evaluates the interlocutor with a high human likeness. So only the ones who perceive the robot human-like are influenced by what the robot is saying. So this opens a lot of things, just to say, the uncanny valley and all these things that, I mean, we can discuss later, but I want to stress the point of the collaboration with experimental economicists, also because they already have this very structured scenario, these structured interactions that are very studied to extract detailed aspects, like trust, this parameter of how collaborative can be, how successful, let's say, how convincing can be a subject to another. And this is very useful if transposed to social robotics, because we can vary features or behaviors of the robot to understand what is happening in its human interlocutor. So it is a good occasion to merge, let's say, techniques of affective computing with models that we think that are good in cognitive systems to perform a reliable behavior, and to see what happens in this interaction. Okay, not just as a behavioral, on the side of decisions, but also by the side of physiological aspects of the body. So this is just a summary of what we have, of what I've talked about. So these are several objectives that we have with Abel. So this integration of affective computing devices. So the integration and test of this novel algorithm for facial emotion recognition. We are collaborating with the CNR for natural language processing, and to construct, let's say, to understand a good ontology and a good way that the robot has to follow to speak to improve the collaboration between a robot and a subject, and its empathy, let's say. Yes, this study is on trust and moral decisions. Now we are writing proposals also for putting these kind of robots inside a group to see what happens in a group decision, so in teamwork. We will surely go on verbal communication also, that we didn't with face, also for, let's say, the possibilities that the mechatronics of the robot gives us. Okay, yes, combined with little body gestures, generation and adaptation of personality and behavior based on the robot's experience and interaction with the human counterpart, and the application of all these things, especially also thanks to the integration of these affective computing devices, to make the robot, to use the robot, let's say, in all these contexts where emotional appraisal or expression is impaired. So, for example, yes, conduct disorder, Alzheimer, attention deficit. So all these situations in which the robot can help, both for a diagnostic aspect and a therapeutic approach in helping a subject in better expressing, or to understand if there is a reaction and what better provokes an emotional reaction in subjects that are unfortunately difficult to study by just a behavioral point of view, by an observation of behavior. Okay, that's it. These are some pictures of a photographer that are following us in this project, and thank you for your kind attention. So,
thank you very much, Lorenzo.
thank you.
No, very interesting, very, very interesting. Thanks.
I will stop sharing the screen. Yes, I think it's better.
Now everyone should be able to unmute themselves. So if you want, I can keep track of the order in which you want to ask questions, but please go ahead, because otherwise I will go and ask like 10 of mine. So I don't want to use my powers. Okay, Martina, go ahead.
Thank you. Thank you so much. Can you hear me?
Yes.
Yeah, yes.
Thank you, Lorenzo, for this very interesting lecture. And I would like to ask a question precisely on uncanny valley effect. Did you test Abel for uncanny valley effect with people?
Yes, not yet. Not yet. This is something that I think that should be immediately done. Yeah. So, but I want to say also something more about uncanny valley, because I mean I didn't face this problem in the presentation, but I was sure that when it comes out in the discussion. I also have. So I will share my screen again, just a slide on these. So uncanny valley is obviously a theory that doesn't have to be underestimated or ignored or neglected, because it's something that is crucial in this kind of robots, especially for the extreme human likeness and realism, no, in the movements, in the aesthetics, and but I would say that I mean times are changing. No, I mean this is a theory from the 70s, and so what is I mean everyone knows in this in this community what is about. But anyway, just to say it is this problem that we have. The more the robot is near to the human, no, in its aesthetics. So we can imagine that the comfort, the familiarity that we have with this robot should increase the more it's similar. But we have this steep drop off because why? So why we have this kind of reaction? There are a lot of hypotheses, but for example, there is one that I don't like, this pathogen avoidance thing. So the fact that you see something that is very similar to you, and so you for your instinct, you let's say refuse this thing because you see some differences, some defects in the movement that makes you think that this has some problems that can be passed through you by I mean biologically speaking. So you have this reaction like hardwired, but I don't think that this is true. And I mean, this is something that you have only in the first reaction, not in the long-term interaction. And this conflicting perceptual truths that I think that is more reasonable. So this cognitive conflict. So it is a categorization difficulty. So I don't know what it is. So it is a human, is it alive or not? I don't know. I don't have the instruments to behave, to interact with this kind of object because I'm not sure what it is. And this is right. And I have also this perceptual mismatch. So I mean that I have expectations of it. No? I mean, it looks like a human. It looks very much and more like a human. So I will have expectations. So I think that there are many critics about the uncanny valley hypothesis that I agree. So one is the fact that this hypothesis is a bit impractical because it's quite impossible to use this likability and this anthropomorphism using just a one-dimensional variable. I think you would agree with this. It depends on cultural context. This is why nowadays we perform these cross-cultural studies. So I answer yes, we have to perform this uncanny valley with Abel, but we have also to compare the reactions in different places, no? So in different cultural contexts. Another thing is exposure to robots. I think that it's very different, the reaction that you have, for example. I mean, the people that are listening to me now, and the reaction that, I don't know, my grandmother or a random person that I take from the street can have in front of a robot. And it depends if I take this person from Japan or from Italy, okay, or from, I don't know, some different country. So I will say that this thing of uncanny valley is, I mean, if we are here, no, with the human and robot with skin, we have two possibilities of climbing the mountain, no, on this side or on this side. So what does it mean? That it's a matter of expectations, that it can be lowered. So you can reduce the expectations, reducing the aesthetics or the human likeness of a robot, or exposing, for example, some robotics. We also did it with Abel. Or so reducing this cognitive mismatch, or they can be better satisfied. Of course, this is something that is more difficult and is probably more related to research and not to let's say to put something on the market, for example. And how can we do this? What is missing here? It's not, I think, the materials. It's not, I think, the mechatronics. It's not, I think, a lot of things that has reached a very high level, but is exactly the cognitive part, meaning that we have to evolve, of course, also the robot movements, but these are fine, I think, so to improve the cognitive capabilities. And I see there is another question. I'll just say the last thing about this. Another thing that is very important, there is a lot of literature, is the aspect of the motor resonance and the following social resonance, meaning that to create a real empathy, to create a real emotional, let's say, not reaction, emotional feeling between two entities, it is fundamental that this entity looks like me. Okay, so there are experiments with robotic arms, with robots that if look not exactly or not so much as the human movement, the human behavior, this effect is not produced.
Sorry, just a comment on the last sentence. It is more a motor resonance more than a shape resonance. I mean, in this uncanny valley, one of the criticisms, as you mentioned very clearly, is the appearance of the robot, which looks like a human, but it does not move like a human. So I think the core of the problem maybe is to find which is the mechanisms that is responsible of the expectations, and to see if this mechanism responsible for expectations is more motor than shape. I don't know if
yeah, I think I get this point, and I agree, and I think that we can do simplifying a division, meaning that the motor resonance is something that is very clear when the robot moves, and this is why the effect of the uncanny valley is amplified by if the subject, the agent, is still or if it moves. So because it adds another let's say difficulty, another mismatch. But the social resonance is not about neither the shape, neither the motors, but more on the cognitive part. I put these arrows just because our brain works like that. I mean, if we think about mirror neurons, no? So it starts from an imitation of movement, but then I see a face.
What I mean is that, I mean, a statue does not generate any uncanny valley.
No.
So this reaction is very much linked to movement, and not and to me not very much to shape. So that even
I
if
agree,
of course,
but I think that. I agree, but I think that the appearance also. I mean, unfortunately, this happens also with people. No, I mean,
no. Appearance is important. I'm not saying that it is not. It is a fundamental aspect. But the uneasiness that you perceive is mostly generated through movement.
I agree.
Somehow. Yes. So and that is the one of the aspects which I think you can investigate very well with your system, but maybe focusing also on this built-in humanity related to how we move. So the two things needs to be considered. Maybe not too much stressing the movement, but also not too much stressing the shape. I don't know what I mean. What I see here is that the mystery is the mix of the two. You cannot easily isolate one of the two and say, so this is the problem, you know. That's
yes, this is something that is a paradox also when you perform experiment, meaning that you can do a very complicated, I don't know, mental process inside the robot, but then you need to test a single aspect. So you have to simplify everything to measure a detailed thing of the system, no? And this is the same that should be done also with this uncanny problem. But I mean, it's very difficult to isolate, no, features, movements.
Well, I have many other questions, but I hope we'll have the chance to talk longer in the future. Thanks. It was very interesting.
We can also let the other people get
sure,
their questions, and then we can harass Loren, if you want to.
Thank you very much for the talk. It was really, really interesting. And just before I ask my question, I wanted to reply to what you were talking about with Giulio. And saying that I feel like it's the hyperrealism that's doing this, both in the looking aspect and the movement. Because even if you have something that doesn't move, just a statue that looks really like a person, it's really weird. And I'm guessing if you have a robot that doesn't look so much like a human, but that looks like it's doing things on its own and having its own person, that would also be a bit weird, I'm guessing. So I think it's the fact that they look so real that we don't know anymore whether they're alive or not. I think that's where it starts to be creepy.
Yeah, on the other hand, you know, statues are beautiful. I mean, a statue does not cause any unpleasant reaction unless it depicts something which is unpleasant. But
if it's a wax statue that really, really looks like a human, it's
true.
weird. It's not like a rock statue. It's different.
Yeah, true. Yes, you're right. Yeah. Thanks.
You had a question, right?
So my question, was
we have other robots that are less human-like.
Sorry?
The question is if we have or use robots that are less human-like than animal.
Oh, this was really unrelated to my question, sorry. So it was about the somatic marker hypothesis that you used, and the way you used it. And is it that you kind of made a memory module that associates the strong emotion felt and the situation that gave rise to it?
Mm-hmm.
Okay, and is it is there one? So that was for face. Is there then kind of one personality defined by the rules that you give about how to interpret the situations? Is it? And it's only one. There's one reaction possible. Or,
no.
Okay.
No. There is not just one reaction possible, but I mean, this using this kind of rules in this kind of systems, they are also called opportunistic rules. So they are rules that you don't know exactly. I said before that you have a better control of how the robot will think or behave. This is partially true, meaning that you will know in generally speaking. So, for example, which is the personality of the robot? I make a very simple example. The robot can be annoyed by a very noisy environment, so simulated an introvert person, or it can be happy to be in a noisy situation. Okay, so this is a very simple thing. The fact is here is that you don't know what will happen. So this is the main difference between a procedural program and a knowledge-based, rule-based program, that you will know what will happen. You will know that the sequence of the input, the sequence of the data. You don't have an exact structure of the environment, so you have a real-world scenario, but you can design these templates, these structured concepts inside the mind of the robot that are needed to pass from something perceived to something that is a fact, an abstract thing in the mind of the robot. But you don't know how I mean, which rule will be activated, and so which chain will be activated, no? Because also the links between the rules, as in the personality thing that I showed you before, are modulated by the internal emotional state of the robot. So, for example, the course of an action, even in the same personality, will take a different path according, for example, to the mood of the robot. But again, the mood is moved by the context. So it is an attempt, let's say, even if simple, let's say, but it's an attempt to integrate, to embed a personality inside a situation, but with its own artificial emotional states. So you have a lot of control about how this emotional state will be moved by the context and by the events in the context. And you have a lot of control about what to do with these emotions that the robot will feel, okay? But of course, there is a big lacking, let's say, a big questions that we have, but we don't have even for humans, that is how we should behave. You know, this is more an ethical questions. I mean, we don't have instructions about a good behavior, but we can perform asking to people how they think about the theory of mind. I mean, the perception of others' internal processing, trying to emulate this in a robot. But definitely not. It's not always the same reaction. It depends on when an event occurs. It depends on how this event modify the emotions, and it depends on how these emotions modify the inference and the reasoning chain.
Yeah. Okay. Thank you. And linked to this, apart from the face expression itself, is there also a way that the emotional state will affect the action and the way the action is performed?
Yeah.
Faster and okay.
This is, for example, again, something minimal but very simple. We have this plane of valence arousal that corresponds to the position of the facial expressions, but we have also the moods. To, let's say, introduce some micro expressions, because what we do, for example, if I am in an elevator taking a conversation, I will smile as usual, no, to a colleague. But if I have a bad mood inside me, this smile would be probably slightly different, okay? Yeah. So we, let's say, give a contribution of the mood in the expressions, meaning that instead of being exactly a happy face, it can be a bit more sad, let's say, okay? So it's produce effectively a slightly different expression. So a micro expression in the expression of the robot that could be perceived from the interlocutor.
Okay, thank you.
Thank you, Loren. Carla, do you want to unmute and ask?
Yes, thank you, Lorenzo, for your talk. It was very, very interesting. I have a question about the module of social emotional architecture, particular. Yes, the three modules of consciousness. If you can explain a little bit more what is different between the proto-self, the middle consciousness.
Yes. I didn't go into. I didn't.
No,
the details.
It's a very huge argument.
Yes.
I know. So just very brief insight about that.
First of all, I immediately suggest to read that books because they are amazing. Also, very well written. Also. And interesting. I think that it can change your view of emotions, decisions, and so on. So this fact of putting their core consciousness, extended consciousness, I want to say is just a representation. So it's just putting blocks of an architecture to trying to emulate this, let's say, theory of mind, okay? So what they are, the proto-self is just, as in humans, is something that is not completely, is completely unconscious, and is something that is related also to very simple animals, to insects also, and it's just the fact that there is a body, there is an agent that reacts to the environment. and the body also in a certain way changes. But this can be viewed in cognitive architecture as a reactive architecture, no? And so this kind of immediate connection and quick connection, direct connection between the sense and the actuation. The core consciousness is something a bit more elevated, and it's something in between before consciousness. So it's no longer, is not still a conscious agent, but is becoming conscious because is the reasoning. So is like reasoning on the fact that I am feeling these sensations, and it's me that is moving in the environment. It's me that is that I am modified by the environment. So the core consciousness is the perception of the change of the proto self. Okay. Mm-hmm. And at this level, for example, you have speaking about emotions, you have emotions in the first level as quick reaction. So the smile in the elevator, let's say. But in the core consciousness, you can see the arise of feelings. So feelings intended also as secondary emotions also. So let's say emotions on emotions. So reasoning on the fact that I'm feeling like this.
So there is like sort of metacognition.
Yes, it's a sort of metacognition. Extended consciousness, which needs autobiographical memory, is something that, and so for example, in our case, the somatic markers, mm-hmm. I don't know, I'm like, oh, okay, I was freezed, but yeah, okay.
No, it's okay.
So the extended consciousness that need memory, that needs, in our case, the somatic markers, is something that is deputed only to humans, let's say, and it's this fact of this narrative, let's say. So this fact of having a story and having a memory that is not so divided by the body, meaning that it's not just factual information, factual memory about data or images, but it's also about how the body felt in that moment. Okay. And the let's say the recall of this sensation is what produce our what Damasio called our extended self.
So okay. it is extended in over time.
It is extended over time. Is extended also over this building, no?
Oh, okay.
But this constructionist view lets you understand that you need the previous block.
Yeah,
for having the other one. No? And if you, for example, if you read Kinds of Minds of Daniel Dennett, that is about consciousness, you can see that this line of consciousness, for example, if you see the species and if you see different cognitive agents, is not, a stair. No? It's not something that immediately appears, but it is given by the appearance in the evolution of tools like emotions and of this metacognition, as you said before, about emotions and feelings.
Yeah. Okay. Thank you so much. That's very interesting.
I can tell that whenever you come to visit, it will be a very interesting day of many hours of discussions because we are all left with a lot of questions. Do we have anyone else from the audience? Loren, you still have the hand raised. Do you have like a follow-up question?
I want also to add another thing, but afterwards.
Yeah. Maybe I wanted to ask, I didn't really understand, you said something about Abel being able to express damage that can happen to him with the inverse kinematic thing. I didn't really...
Oh, no, this is just something very simple. So it's just having a URDF, so a model of the body of the robot, because being unique, I mean, there is this is the only Abel that exists and have been, let's say, handcrafted. So we don't have like the CAD files of the entire structure of the robot. So we have to take measures to understand the length of the links, the possibility of the joints. and from there reconstruct a model, a 3D model of the robot, and perform some inverse kinematics to avoid that, for example, having not a perception of his own body, a movement of an arm will hit the other arm or the body itself. So we just use a ROS module to, let's say, to design. You can also put, for example, objects in the environment that has to be avoided. And so these inverse kinematics just calculate a motion strategy to, for example, avoid collision with objects or with the body, the self body of the robot. It's just that. I mean, we have to perform, for example, a precise direct kinematic that we don't still have. So the inverse thing. So if you want to reach a point in the space, you have you want to, that the arm is disposed in a way to reach this point, and so on. So I mean, this is basics, fundamentals of robotics and control.
Thank you.
Adam, go ahead.
Yeah, maybe I missed it during the presentation, but you mentioned something about the attention module that you have created. How does it exactly work?
Okay, this has been done with a human-human interaction approach, meaning that to understand that there was a precedent. I mean, this is a bit brief story, but I will say that we have another student working on that, and he did this procedural approach in which every subject has a score for attention, and the one who has the highest score wins the attention of the robot. And this score is given by the distance, is given by the fact if he's speaking or not, and this is the procedural approach. Then we perform another thing that is putting subject with an eye tracker where so these glasses to see and to understand where the gaze was going, and we put this subject in a real social scenario. So in a room, in a lab, in which people entering, which people speak to him, or I mean things happening in the context. So then trying to understand a sort of priority list of these actions in the context. For example, we realize that if you are in a room and there is a door in your field of view, and the subject is entering or exiting to that door, your attention for just a short time will be captured, and then you come back to, for example, a subject that is speaking to you. So how did we apply this? Again, with the attention model, so the rules deputed to this control, giving, for example, different saliency to these actions, but keeping it very free, meaning that again, you have these opportunistic rules. So if something happened in the environment, probably is in the agenda, in the inference engine, would be discarded because it's not so important. But if it's important, it will be competitive with another rule that is activated. So, for example, I have a person that is raising a hand, but I have another person that is crying. So again, this is design of personality, design of behavior, which will deserve more attention. So one thing is the instinctive, unconscious thing, and one is the, let's say, a more designed and forced behavior that you can also apply to the robot. So this is what we mean with attention model. Then, of course, you can use a machine learning approach. We have, for example, talked with a professor from Politecnico di Milano that they use another approach. So they have a data set of scenarios and scenes of social interaction, and you extract from there where the subject is looking at. So you train, let's say, a gaze. I mean, but just as a point, of course, in the image according to this training data set.
Okay, maybe a follow-up, but this is all based on the sensory data that you capture from the environment. But does the robot, the actions that the robot do, influence its attention or not, in your case?
Oh, I would say no, meaning not directly, not in the cognitive systems, but yes, in the social loop, because of course, an action of the robot, like the robot speaking or the robot looking at the person crying, would make the robot, the person probably stop crying, and so these things will be recalculated again from the processing system because the situation changes, and we have let's say a refresh of 300 milliseconds. So every 300 milliseconds, a new situation, a new feature that started from that situation is given to the robot. So I would say not inside the cognitive block, but inside the situation, and perceived again, we will see surely some change also in the behavior.
Okay, thanks.
Thanks to you.
A very brief follow-up on this one for the attention. Do you use just, I mean, the perception signals from the cameras, or do you also use auditory?
No, we use both. We have, for example, the speaking probability that is simply given by the cross information between where for example, the head points or given by the keynet and the source, so the highest source of sound. You know that, for example, the keynet have this array of microphones, so you can detect from where the sound is coming, so you can see if there is a person in that location, and the speaking probability of that subject would be high. So yes, for audiovisual, yeah.
Thank you. I think that considering that it's been over an hour and a half, we can start to wrap this up. Lorenzo's email is already shared, I think, in the first.
Yeah,
I think on the abstract and bio it should be, but if not, I will update it. So you can also email him with all of your questions. And I think we will be very, very happy to host you in about a month's time. We need to finalize arranging when we will have you and Enzo visit us in Genoa. But so we will have a follow-up event, and you can very, very much come and ambush him and ask all of the questions you want. But
okay,
in person,
thank you again
so
for this invitation.
Thank you very, very much for the talk, Lorenzo. It was incredibly interesting, and we look forward to our next one. Thank you, everyone, for participating, and take care.
Ciao.
Thank you. Bye, everyone.
Bye.